So this is practical number 10, analysis of 2 cube factorial experiments in RBD, partial confounding. So this is the first example that we are having. Analyze the following design. In this we are having data like this: replication 1 which contains block 1, block 2. Replication 1 we are having divided in two blocks. Similarly, replication 2, replication 3 and replication 4, all those replications, they are divided in two blocks. So what we have done, like in the previous case, we have written this 1 nk nkp np kp nkp, this in the serial order, and the corresponding values in those replications here. 1 2 3 4, these are the replications. In those replications, what is the value of 1 that we have taken from this data? See, in replication 1 takes value here 10, so that value we have taken here. From replication 2, it takes value 1 takes value here 23, so that value we have taken over here 23, and likewise all these values we have taken for all the replications for 1 and for all the treatment combinations. Then total we have obtained. This we have done in the previous practical also. So by using this totals, once again we write the treatment combination by following the order here: 1 n k n k p n p k p n k p, like this. The totals what we have obtained in the previous this slide, this will take here, and we apply the Yates method here for getting the sum of squares. So what we are doing there, we are adding this first value, we are writing this value in the first here, then add the next two values, third and fourth value will write in the second place, fifth and sixth value write in the third place, and seventh and eighth value, its addition we write in this place. So first half of this table, this column, we are adding the pairwise values here, and in the second half we are subtracting the once again the same pairs. Only what we have to remember here, we have to subtract the first value from the second value, third value from the fourth value, and fifth value from the sixth, and seventh value from the eighth value, and we'll get this values here. Same procedure we repeat for column number 4, column number 5, and whatever we get here, this is first value, this is, we call it as G. J is the grand total, means total of all the observations. Okay, capital N is this corresponding treatment combination, its total we are having here, this is nothing but here. Okay, then we obtain sum of squares here. So bracket square means square of this divided by 32. Why 32? Because we are having 32 observations here, 32 here, 8 observations here, and such 4 replicates we are having, so 32 observations. So because of that we divide here by 32. So we have got this first term, G square upon n is the total number of observations, that is correction term actually. This is n square divided by 32 means this 22 square divided by 32 will get this value, 44 square divided by 32 will get this value. These effects, they are confounded in those blocks, so we keep those, we are not writing here those totals, the sum of squares here, that has the different procedure here. For P we have obtained this here. What is confounding? Firstly, what confounding means, what for some of the factors we are not having information related to that, so those actually those are confounded in that corresponding replication, that is the thing here. So how to identify firstly the which treatment combination gets confounded in which replication? So it's method that to get which factor gets confounded here. So what you have to do here, you have to see this two blocks we observe. corresponding to block 1 we are having 1 is present over there. We are not observing that block. Other than 1 where it is not present, that block we observe. And here the single factors that we see here, N, K, P, these are the single factors we are having. So in this replication, this NKP, this treatment combination gets confounded in replication 1. Similarly, in this second replication, other than this one, in block 2, we are having 1. So we observe block 1. In block 1, observe the single factors here, K and P we are having. So its KP is confounded in the second replication. This is meaning here. Okay. Similarly, in replication 3, observe other than the 1, that block is this one here. So N and K, these are the single factors. So NK treatment combination that gets confounded here. Here in replication 4, other than this one, we are having this NP gets confounded here. Single factors are N and P. So NP, this treatment combination gets confounded. So here NKP, here KP, here NK, and here NP. Such a way this confounded treatment combinations we get, means all these 4 gets confounded here. So because of that, we are not writing sum of squares over here. Okay. Then how to get this sum of squares calculated here when we are having confounded? Here partial confounded here. What is meaning of partial confounded here? Means in all the replicates different treatment combinations get confounded, then we call it as the partial confounding. If in all the replicates the same treatment combination gets confounded, then that is the total confounding. Here in all the replicates we are having different treatment combination confounded. So because of that, this is the problem of partial confounding. So what we are having here in partial confounding, we are not losing the whole information related to that treatment combination which is confounded. We lose information of that confounded factor in that replicate only, but we can get the information related to that confounded factor from the remaining replications. So we can find out those values, those sum of squares in partial confounding. Okay. So how to get this values that we will see here. From the practical point of view, sum of squares for confounded effects can be obtained from the given table of Yates method. So how to obtain that? For all 4 replications by applying some adjustment factor. So for all those replications we are having, we apply some adjustment factor to the confounded effects. The adjustment factor for any confounded effect is computed as follows. Okay, so how to get that adjustment factor, that we will see. Firstly, what we have to note here, note the replication in which the given effect is confounded. Means what? We have to identify in which replication which factor gets confounded here. Here in this first replication we are having NK gets confounded. Such a way we have to note down which factor confounded in which replication, that we have to note down here. So that is the first thing. Then after that, what we have to do here, note the sign of 1 in the corresponding algebraic expression of the effect to be confounded. Means when we are writing that term here, this suppose NK that is confounded somewhere, that we are having that algebraic expression over there for that NK. By observing the sign of 1 in that we observe here, and from that sign of 1 we decide how to find out the adjustment factor. If the sign is positive, sign of 1 actually, sign of 1 is positive in that expression, algebraic expression, then what we do here, adjustment factor is computed here. Total of block containing 1 of replicate in which the effect is confounded. Okay, total of block containing 1 where this 1 is present, total of that block, corresponding block, we find out where in which the effect is confounded, minus total of the block not containing 1 of the replicate in which the effect is confounded here. Okay, so we call this first term as T1 where the 1 is present in which the replicate is confounded in that replication, so that we call as T1, and where 1 is not present, not containing, that we call as T2. Such a way we find out the adjustment factor. When this we are obtaining, if sign of 1 is positive, then we are computing this way. If the sign is negative, then we compute adjustment factor equal to T2 minus T1. Where we get T1 minus T2 in all the combinations like this NK, NP and KP. Okay, we'll get here positive sign, but in case of NKP we are having their sign is negative over there. So remember this thing here, in NKP you are having that factor 1 by 8 into bracket A minus 1 into bracket second bracket B minus 1 into third bracket C minus 1, minus 1, minus 1 and minus 1 everywhere. So its multiplication finally you are getting that as negative in case of NKP. Okay, so sign of 1 is negative there only. Other than that we are having positive sign. Other than that means that where this we are having confounded here, means NK, NP and KP. In those case we are getting sign of 1 is positive over there. So in that case we use this, and in case of this 3 NKP is confounded, then in that case we use this formula T2 minus T1 here. The adjustment factor will be subtracted. After getting the adjustment factor, what we do, adjustment factor will be subtracted from the factorial effect totals of the confounded effects obtained from the Yates method for all the 4 replicates. So what we do here, adjustment factor will be subtracted from the factorial effect totals of the confounded effects obtained from Yates method for all the 4 replicates, or all 4 replicates we are having in this case. So we subtract related to that from the factor here. So how we are doing here, see, those blocks we are having, I call those blocks as 1 to up to 8 here. Every time in the example we are having block 1, block 2, but I have given the next number. This is block 3 means it is replicate 2. Block 4 is also block 2 of replicate 2, and such a way we are having this is replicate 3, block 1, block 2, replicate 4, block 1, block 2, like this. Their totals we have obtained here. Totals how we are obtained here? This way here. Total of this 10, 18, 14, 17, that is total of block 1, and that value we are having is this value. Such a way all the totals we have obtained. Their squares we have done because of obtaining the block sum of square. We require the sum of squares of those block totals. So squares we have obtained and its sum we have obtained here. Okay, this we are having here. Then it's the problem to obtain the sum of square related to the confounded factors. So we'll write those treatment combinations. Which treatment combinations? Those are confounded. So we have written NK, NP, KP and NKP here. So where NK is confounded, that we'll see there NP, KP and NKP. That we'll see in which replicate it is confounded. Just see first one, first replicate NKP is confounded here in the first replicate. So we have written here NKP, it is confounded in the first replicate. So in that case we are obtaining T2 minus T1, this way we are obtaining there. And for the this, just see here in replicate 2, other than 1 we have to observe KP, it's confounded here. So we'll have here in this 2, we are having KP gets confounded in such a way we are having NK and NP in third and fourth replicate. They gets confounded over there. So we obtain by T1 minus T2, T1 minus T2 in this 3 for this 3 treatment combinations and NKP for the this combination here only. That is T2 minus T1 we obtain here. Sign of 1 we are having plus 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 and here minus, so because of that we are having this here. That also we have noted here. Total of block containing 1, that we call as T1, and total of block not containing 1, that we call as T2. So we have to go there and we have to find out this where 1 is there. See, for example, I will explain this. NK is confounded in third replicate. So what we see, where 1 is present in which block? Here in this case NK is confounded in this replicate. So in block 2 1 is present here. Block 2 means whatever totals we are having, that is here 1 2 3 4 5 6 block total becomes T1 and block number 5 total it becomes T2 there. So we are having this here. Block number 6 its total, block number 6 its total is this 109 and block number 5 its total it becomes T1. How we got this? Where 1 is present, that we call, that total of that block we call as T1. I will show you for the next second one here. NP. NP is confounded in the fourth replicate. So we'll see here. NP is confounded in the fourth replicate here. NP is confounded here. So where we are having 1? We are having 1 in block 2. 1 in block 2. So once again this becomes our T1, where 1 containing 1, that we call as a T1, the total of that block means total of 8th block. This block 2 means 8th block. We have ordered serially, so this becomes 8th block. That total of 8th block it is T1 and total of 7th block that becomes T2 for this corresponding treatment combination. Total of 8th block, that is 88. See here 88, that is T1 and total of 7th block, that is T2 here. Such a way we have obtained all these values here. Okay, T1 and T2 we have obtained. Then here we have to obtain adjustment factor. Adjustment factor we are applying this T1 minus T2. So 109 minus 68, that we are having this. 88 minus 99 we are having minus 11. 87 minus 66, 21 here. And in this case T2 minus T1 we want to do. So 90 minus 59 we are having 31 here. Then sum from table. The sum from table means what? Which table? This table here. Actually this values here. This Yates table actually. This is sum of NK. 52 we are having. So that we have taken as 52 for NK. NP its sum we are having in the table, that is 8 here. We have taken that 8 over here. For KP we are having 18 and for NKP we are having 38. Just see, KP we are having 18 and NKP it is 38. Then how we get factorial effect total? We are subtracting the adjustment factor from this whatever total we are having from the Yates table. So 52 minus 41, that is 11 here. Then 8 minus 11 it gives us 19. 18 minus 21 it gives us minus 3. 38 minus 31 it gives us 7. Such a way we get the factorial effect total by subtracting the adjustment factor here related to this treatment combinations which are confounded in the different replicates. And sum of squares once again we obtain by our usual way. How we are doing that? Square of this divided by, in the previous case we have done divided by 32 here there, but here what we are having, this nk gets confounded in one of the replicate. So what we are having here, we are losing information related to that nk in that corresponding replicate. So whatever information we are having, means this total we are having, this total we are getting from the remaining 3 replicates. So because of that, the remaining 3 replicates, they contain the 24 observation. 8 into 3, 24 observation. So because of that, we are getting this factorial effect total from the remaining 3 replicates. So because of that, what we do here, square of this divided by 24, in which how many we are having gets that gets confounded, where those many we subtract, means here we are having in one of the replicate it gets confounded. So because of that, we are not taking those 8 observations. So remaining 24 observations we take, and its divisor we are having as 24. So 11 square divided by 24, it gives us this value. 90 square divided by 24 is this value. For all this, we are having the same rule we are applying, because in each replicate one of the combination, treatment combination, gets confounded over there. 3 square divided by that 24, we are having this. 7 square divided by 24, it gives us this value. So these are the sum of squares related to this treatment combination. Because of the partial confounding, we are getting this sum of squares. We are not losing the whole information here. So because of that, we are getting this totals here. In total confounding, we are not taking that factor in ANOVA table itself, but here we are not losing whole information. So because of that, we are including this treatment combination. Still they are confounded in our ANOVA table. Total sum of square that we obtain by our usual method, double summation xij square minus ct. Double summation xij square means this 32 observations we are having. Just 32 observations. Square each observation, 10 squared plus 20 square plus 30 square, like this, plus 90 square. All these 34 observations, square each and every observation, take its sum, that is double summation xij square, and minus cf is this value 13861.125. That is the value of correction term or correction factor that we have written here. Take subtraction here, we'll get this value, that is the total sum of squares. Then block sum of square, that is bj square divided by 4 minus ct here, correction term once again. How we are getting this bj square divided by 4? This value we are having, this 57556. This is the total. We have written this total here, and while taking this bj values, block totals, when we have taken, we have added 4 observations only. Okay, so because of that, we divide here, divided by 4 here, and minus correction term, that is this value. So we get finally this value here. Treatment sum of square is nothing but sum of squares of each and every combination, treatment combination, nkp, nk, np, kp and nkp. All this we have added, and we get this as the treatment sum of squares. Error sum of square can be obtained by subtraction, total sum of square minus block sum of square minus treatment sum of square. So we'll get this as the error sum of square. So we get all the sum of squares here. We put the information in the ANOVA table. ANOVA table, we are having sources of variation here. Source of variation, in that we are having blocks. Treatment, actually this is treatment here also. Okay. This is treatment here, NK, NK, P, NP, KP, and KP, error and total. So total we are having 8 blocks, so 8 minus 1 we are having 7 here. Total 32 observations minus 1 we are having here 31 here, and 7 treatment combinations, 1, 2, 3, 4, 5, 6, 7. So because of that, they are having 1 degrees of freedom, and treatment degrees of freedom, it becomes 7, because those treatment we have divided in the this different factors we are having NK, NKP, like this here. So we are getting that as the degrees of freedom related to treatment. Then this we get by subtraction, 31 minus 7 this block and minus this treatment degrees of freedom. So we subtract from 31 that 14 degrees of freedom, will get this as 17 here. Sum of squares, what we have obtained this in the previous case, those we substitute there. Total sum of square, block sum of square, treatment sum of square that we are having as the specific treatments we have considered. So we write those values over here in sum of squares column. All those we have substituted from that values. Mean sum of square can be obtained by sum of square divided by its corresponding degrees of freedom. So we get this divided by this, we are having this value. This by 1 we are having, so we will get the same values. This divided by 17 will get this one here. Then we obtain F ratio. How to get F ratio? F ratio, while obtaining F ratio, corresponding factor divided by corresponding mean sum of square related to that factor divided by mean sum of square due to error. So this divided by 32.61 here, we'll have this one here. This divided by this, we are getting less than 1 here. So what we do? We do 1 upon f here. So this we get by 1 upon f here, because of this is less than this one here. So because of that here, while obtaining f table value, we reverse the degrees of freedom also here. In this case we require 1 and 17, but we have seen this as 17 because of 1 by f here. Here we will get this is larger than this one, so we have done only f here. 60.5 divided by this term, we'll get this one here, and we are having this f table value is 1 and 17 here. Here this all these values, they are less than this value, so while obtaining this f ratio, we have taken 1 upon f here. For this case, everywhere we have done 1 upon f. So because of that, we are having f table value is f 17 same value here. And if we compare all these values with this table value, everywhere we get the hypothesis accepted, nowhere it gets rejected over here. So all hypothesis gets accepted for blocks also and for treatments also. Those values I have written here. Table values F117 is this, F4717 is this value, 17.1 is this 247. So we write the hypothesis for blocks H naught B. It is B1 equal to B2 equal to B8 equal to 0 here, and H1B blocks differ significantly. The test statistic is F is equal to MSE upon MSB, which follows F with 717, that is this value here. We are having calculated value as 2.31. Since F calculated less than F this table value, we accept H naught at 5% level of significance, that is the blocks do not differ significantly. Similarly, we are having this treatments, different treatments here, statistic for different treatments here, and these are the hypotheses H naught n for n equal to 0, k equal to 0, and k equal to 0. For all this we are having treatment combination. These are the hypotheses, these are the test statistic we are having, and just now we have seen in the table, ANOVA table, all the hypothesis gets accepted here. We are having this is the decision rule. So we make conclusion from this, all treatment effects N, K, P and KP, NK, NP and NKP are insignificant because H naught is accepted in all the cases. So because of that we are accepted. This is the second example. You have to perform in the similar manner.